This talk is brought to you by the Bamberg Mathematical Consciousness Science Initiative.
Okay, thank you very much for inviting me. Today I'll be talking about both mathematical phenomenology and computational phenomenology and their differences. Oh, wait a minute. Let me see. Unfortunately, the images of everyone. Oh, I can put it up here. Very good. Okay, so this is an outline of what I'll be speaking about today. Because computational phenomenology is terminology defined by the active inference community, first I'm going to give you a brief mathematical overview of active inference, which is a framework for neuroscience and artificial intelligence shaped by scientists sympathetic to phenomenology. And then we'll focus in on computational phenomenology as it's defined by this community. Then we'll talk about mathematical phenomenology and how it's different from computational phenomenology. And finally, I'll give you some examples of mathematical phenomenology and some potential future directions. So these are my four main points, especially number 3. Active inference models are often described as phenomenological due to targeting subjective experience. But active inference is a scientific theory utilizing non-pre-theoretical constructs. Computational phenomenology is potentially confusing terminology. I would suggest an alternative term, computationally inspired, phenomenologically inspired computation. The third point is that a purely descriptive, non-predictive mathematical phenomenology is possible and should be clearly distinguished from scientific theories of phenomenological experiences. And finally, we'll conclude, I think Jeff's type signature for Husserl's horizon is the paradigmatic example of mathematical phenomenology. So we'll look at that in detail. Now, let me be clear. There are no claims I'm making which should offend active inference practitioners and enthusiasts. Any such offense would only be due to my inability to make clear the limited scope of my claims. And I always use phenomenology in the philosophical Husserlian sense rather than an informal colloquial sense, which has become more popular in recent years. All right, so with that, let's dig into let's do a lightning introduction to active inference. As I said before, active inference is a framework for neuroscience and artificial intelligence, and it has two main fundamental principles. The first principle is that agents acting in the world want to minimize their surprise by either updating their model of the world or acting on the world to change it, or both. The second fundamental principle is that agents want to infer the hidden causes of their sensory experiences, i.e., objects in the world. So in active inference, perception is conceptualized as unconscious inference. Now, what are the mathematical tools which active inference employs? They're called graphical models. Graphical models consist of nodes labeled with random variables and directed edges, which express dependency relationships between these random variables. Now, it's very important that these random variables are divided into two groups, observed and latent, also called hidden. Hidden states can only be inferred from observations. They're by definition unobservable. So this little picture here is an illustration of a very simple graphical model called a hidden Markov model, where the shaded nodes labeled with the O's are observable nodes, and the unshaded nodes labeled with the H's are latent variables, hidden variables. The primary goal in graphical models is to infer the values of the latent variables from observations using Bayes' theorem. So that's the fundamental mathematical background which we need for active inference. Now, recall the first fundamental task is to minimize surprise, which is mathematically defined as surprisal, which is the negative logarithm of the probability of the observations, where the probability of observations, if you remember, is the denominator in Bayes' theorem. And this is called the model evidence. Recall the second fundamental task is to compute the posterior, again, using Bayes' theorem, which also requires computing the model evidence because it's the denominator. Now, it turns out that the model evidence is hard to compute exactly, as it's a sum over potentially exponentially many latent states. This is a problem for both computational modeling and also the brain, if this is in fact what the brain is doing. So how are we going to solve this problem? It turns out we can approximately accomplish both goals by finding a distribution Q called a variational distribution, which minimizes a quantity called free energy. Q approximates the posterior, and free energy is an upper bound for surprisal. So by choosing a variational distribution which minimizes free energy, we accomplish both tasks. And this is computationally tractable. So in brief, this is active inference in a nutshell. Now, what is computational phenomenology as defined and described by this community? I think this quote summarizes it quite well. Our approach can be described as computational phenomenology because it applies methods originally developed in computational modeling to provide a formal model of the descriptions of lived experience in the phenomenological tradition of philosophy. That's a pretty good working definition. So if this has all been too abstract, this is a simple diagram. Well, maybe not so simple, actually. This is a diagram of not only an active inference model, but one that qualifies as being a model of computational phenomenology, because it aims to formalize meta-awareness, which controls attentional states, which itself controls perceptual states. So this particular diagram is a little different than the one I showed you before. Here, the unshaded circles are the observable random variables. The shaded circles are latent variables, which have to be inferred. And the squares, which didn't appear earlier, represent the parameters which define the joint distribution described by the model. So this is what a typical computational phenomenological model would look like. And I want to point out that these parameters they didn't come out of nowhere. They were derived or specified through experience. Okay, so now we come to my objections about this terminology of computational phenomenology. So models in computational phenomenology contain latent variables, i.e. unobservables by definition, and therefore these models are scientific and predictive, and not, strictly speaking, phenomenological and descriptive. Also, consider any scientific field labeled computational X, for example, computational biology. In computational biology, we use computation to learn new biology. However, we do not learn new phenomenology from active inference models. Rather, these are predictive models which are motivated by and defined by experiential insight. The flow of information in computational phenomenology goes from the phenomenology to the formulation of the model, and not, as one might suspect, from the model to the phenomenology. So I suggest phenomenologically inspired computation is more appropriate terminology. This is in no way a criticism of active inference models or the overarching scientific project, but just rather the terminology, which is likely confusing to a phenomenologist. Now, is this just terminological nitpicking? Does it really matter? Well, I'd like to convince you that it's not nitpicking. First of all, there are important differences between predictive scientific theories and phenomenological descriptions. This is absolutely central to Husserl's philosophy and to the practice of the epoche. But more specifically and practically, we will discuss a sharp contrast with what I'm going to be calling mathematical phenomenology. So let me summarize. Active inference is a mathematically fascinating framework for intelligence and agency, populated by scientists sympathetic to phenomenology. As far as I know, it's to date the high watermark in terms of the influence of phenomenology on the scientific domain. But let me summarize my concerns. Active inference models are often labeled phenomenological models because they are applied to conscious experience, but they make essential use of unobservable variables. Secondly, information propagates from experience to model and not from the model to experience, as you might expect from the computational X terminology. So computational phenomenology could be considered confusing for these reasons, but does it really matter? After all, it's just terminology. But what matters, in my humble opinion, are the contrasts with what I'm going to be calling mathematical phenomenology. So what is this thing? Let's tentatively define mathematical phenomenology as the use of mathematics to illuminate experiential structures without straying from direct experience, for example, in the form of latent variables. Now, what's the advantage of this? Why would you want to do this? Well, mathematics provides precision, clarity, and communicability. Let me give you an example for the formalization of symmetry. As children, we all learn about symmetry at a very young age, probably when we first start drawing fixed stick figures of human bodies, which have symmetry. But the mystery, beauty, and profundity of symmetry requires formalization in group theory. You can't stay at the informal level. Now, this definition in the previous slide is probably too general. There are many examples of mathematics formalizing aspects of experience. For example, we formalize nearness in topologies. We formalize distance in the form of metrics. We formalize same-sizeness in the form of bijections between sets. So let us restrict our attention to considering strictly formalizing Husserlian structures, especially constitutional structures, for example, the horizon. There are many examples of mathematical phenomenology in the literature which conform to this definition. For example, in Husserl and intentionality, Smith and McIntyre use possible world semantics to define to describe intentionality. In mental representation and consciousness, Marbach invents a graphical notation for representation. In morphological eidetics, for a phenomenology of perception, Petitot uses differential geometry for Husserl's theories of visual perception. In formal structures in the phenomenology of motion, Casati axiomatizes rest and motion. In Noemat and their formalization, Christofiak, I'm not sure about that pronunciation, axiomatizes noemata. And in Husserlian phenomenology, a unifying interpretation, Jeff formalizes the horizon as a type signature. And I'm sure this is not a complete list. I'm sure I've missed some. Now, all of these examples, except the last one, have a flaw, which is that they all use either sophisticated or fairly sophisticated mathematics or sophisticated phenomenology or both. And that's why Jeff's use of a type signature for the horizon is my favorite go-to example. Now, Jeff kind of stole my thunder by introducing what he actually wrote about, but let me recover some of this. So first of all, let's make sure we're all on the same page about what Husserl's concept of the horizon is. The horizon of an object consists of anticipated potential future experiences of the object. So if I'm looking at the front of a white house, I know that one way to further explore the house is to walk around the back of the house. And I expect to see the back of a house painted white. I might end up being mildly surprised in seeing that it's painted red. Or I might end up being shocked and it's not a house at all, but it's a movie facade. So this is the notion of a horizon. Every object comes equipped with a horizon. Now, Jeff formalizes this notion as a function signature or a type, as it's known to computer scientists. Which means a function signature or type just specifies the nature of the inputs and the outputs. So as Jeff had briefly described, the inputs to his horizon function are three kinds. It takes background knowledge, the current visual image, a potential movement, and it outputs a probability distribution over future visual images. And the reason why this is my favorite go-to example is because it's straightforward math and phenomenology. A function signature is well known to mathematicians, computer scientists, and programmers. And the horizon of an object is about as basic a phenomenological concept as you might desire. And so it's a perfect example to show to your friends when you want to describe mathematical phenomenology. Now, I also want to mention Jeff's learning rule, which he also mentioned, lambda, which takes 4 inputs, returns 1 output. And the inputs are as follows. It takes background knowledge, the current visual image, a potential movement, the future visual image, and it returns a new piece of background knowledge. So this is a knowledge update rule. And this will become relevant in the next slide. So what's nice about what Jeff has done here is that formalization is an opportunity for precision and comparison. So for example, in this first bullet, I've just reproduced the previous slide, what Jeff has defined. Now let me propose our first alternative. When you walk around the back of a house, what you see is not independent from how you're going to update your knowledge. And so you could argue that there should be a joint distribution over the new visual image and the new batch of knowledge. So you could formulate this as a function with the following signature. I'll call this function h lambda. It takes the same inputs as Jeff's h function, but the output is a joint distribution over the knowledge space and the visual image space. Now we can also formulate another alternative here, which is actually mathematically identical but philosophically different. We might be somewhat uncomfortable with talking about a subject with knowledge. This might be a little bit too much cognitive science and too little phenomenology for us. So we might want to throw what we've been calling knowledge, all of it outside, into the object. And so all we do is replace the knowledge space with the object, some sort of object space. So like I said, it's mathematically identical, but philosophically distinct. Now, the point here is not to argue, not that one of these is the best or the right one. The point is that without formalizing this, it's virtually impossible to even make these comparisons or even begin to have an argument, right? So this is why I think we want to formalize things whenever we can. Let me talk about some possible future directions in mathematical phenomenology. In his excellent book, Introduction to Phenomenology, Sokolowski indicates 3 structural forms threaded through Husserl's work: the structure of parts and wholes, structure of presence and absence, and the structure of identity and multiplicity. Now, for the structure of parts and wholes, This has already received significant mathematical attention, and I refer you to Varzy's recent book on mereology. For the structure of presence and absence, well, this is closely related to the horizon work that we've talked about, fulfilled and unfulfilled intentions. So Jeff has already made a start on this, but I really feel as though there's a great deal more that could be done here. I'm not exactly sure what direction, but there's a lot of potential here. For the structure of identity and multiplicity, this is my favorite of the three, the one that fascinates me the most. Does identification of multiple immanent content possess mathematical structure? In other words, can we mathematize the constitution of transcendent objects? So let me conclude in the next few slides by throwing out some half-baked mathematical ideas. We'll start by describing identity types in homotopy type theory, because I find this inspirational for identity and multiplicity. In the traditional foundations of mathematics based on set theory, equality is trivial and uninteresting. Two things are either equal or they're not. In homotopy type theory, equality, also called identification, is highly structured and very interesting. So what is homotopy type theory? Well, homotopy type theory is based on what's called dependent type theory. Dependent type theory is an alternative to set theory as a foundation for mathematics. And homotopy type theory itself is just dependent type theory with some other stuff thrown in, namely the univalence axiom and higher inductive types, about which we won't talk about. In homotopy type theory, there are these things called identity types, which express not only the fact of two things being the same or identified, but also how they are identified. Things can be equal in more than one way. In hot, identity things are called infinity groupoids, and identifications are called paths or homotopies. So with this as inspiration, let's take a very preliminary shot at formalizing the constitution of transcendent objects. Let's call a pre-object a pair consisting of a visual image and a visual horizon function h, where the visual horizon function encodes the probability of seeing a particular image from a hypothetical location and orientation. So the input to h would be a location in space and an orientation, and it would output a distribution over visual images, similar to what we've seen before. Let the space of these pre-objects, call it T, define a phenomenological visual experience as a function which represents a path through space, orientation, and the space of pre-objects. Finally, let a formal transcendent object be the projection of this path onto T. Therefore, the unity of a transcendent object in its experienced immanent diversity is mathematically expressed as a path, which echoes identity as paths in homotopy type theory. So listen, thank you very much for inviting me. It's super exciting to witness the growing influence of phenomenology in consciousness science, and especially mathematical phenomenology. Thank you very much.